In this lesson, we'll explore two additional thermal analysis blocks that are currently in the Beta tab. We'll begin with a transient thermal analysis of the brake disk we used in the previous lesson. Then we'll cover a nonlinear thermal analysis of the same disk. Let's begin by adding the transient thermal analysis block to our notebook. We'll open up the Beta tab, and in the simulation section, we can add a block for transient thermal analysis. Notice that, like the thermal analysis block, we have an input for a model and our boundary conditions. But since the transient analysis is time dependent, we have an end time input, an initial time step, and an output step. This output step is an integer that specifies how many iterations of the analysis are saved. An input of 1 will save every iteration, an input of 2 would save every other, and so on. For our FE model, we can use the same model that we used for our initial thermal analysis. I'll drag this model into our input, and I'll create a boundary conditions list to use as our load case. I'll make this into a variable called boundary conditions transient thermal analysis. I'll add 4 inputs, and our inputs will be the same as those from our original thermal analysis. I'll just copy and paste and pull these into our new variable for visibility. I'll input this into our transient analysis block and set our time inputs with an end time of 2 seconds, an initial time step of 0.1 second, and an output step of 1. This block will automatically run, and I'll go ahead and make this a variable called Transient Thermal Analysis. After the analysis runs, we can view the results in this window to the right, which will look similar to our thermal analysis results. We can view temperature, heat flux, and thermal reaction flux, and view the results at each solution step. Again, we can edit the color settings and use probe mode to view results at individual mesh elements. Now let's run a nonlinear thermal analysis of this same disk. For the nonlinear analysis, we'll need 2 additional material properties, conductivity and specific heat of the stainless steel. Therefore, we'll need to create an entirely new FE model for this analysis. Let's begin by defining our material. We'll scroll up to our brake disk materials section, and we can add a block for an isotropic material. I'll make this a variable and call it stainless steel nonlinear. In our properties list, we'll add isotropic thermal properties. Since our thermal properties are affected by temperature, we'll need to define both conductivity and specific heat using 2 dictionary blocks. These blocks each have scalar lists comparing material temperature and the associated property. We'll drag these blocks in as our inputs. And now our variable is ready to be used in an FE model. Let's add a nonlinear thermal analysis block to our notebook using the Beta tab under Simulation. We'll then add an FE model block to our notebook And we'll make this a variable called FE model nonlinear analysis. In our components list, we'll add an FE solid component, and we'll use our FE mesh of the brake disc as our solid mesh, and our new stainless steel material with the conductivity and specific heat defined. We can use the same boundary conditions as we used in our transient thermal analysis. And I'll call this boundary conditions nonlinear analysis. I'll drop these boundary conditions in as our load case and pull in our FE model. I'll set a maximum of 10 iterations, and I'll choose an output step of 1. We'll make this a variable called Nonlinear Thermal Analysis. After the analysis runs, we can view the results in the right side of the screen, and we have our 3 thermal analysis options to choose from, as well as a solution step slider to view results at certain steps. Now we've completed our advanced thermal analyses, and you can download the completed file as a reference.